So let's talk about Mars. But to really get it, we're going to have to go way back, like 400 years back. We're going to see how the biggest secrets of the Red Planet were cracked long before we ever sent a single rover, using not much more than a sharp eye and some brilliant, brilliant math. I mean, you've seen those incredible pictures that come back from Mars, right? We have these amazing car-sized robotic geologists like Curiosity and Perseverance just cruising around the surface, zapping rocks with lasers, and digging for clues about ancient life. It feels so immediate, like we can almost reach out and touch it.
But that brings up a wild question. What happens if you take all that away? No rockets, no advanced robots, no supercomputers, not even a basic telescope. How in the world did we first figure out the basic roadmap of Mars? How did we chart its epic journey through space? Well, that's the puzzle we're going to piece together.
Okay, so this is where our story really kicks off, with what has to be one of the biggest headaches in the history of astronomy. I want you to imagine you're on a boat, and your job is to draw a map of another boat, but both boats are moving and there's nothing but open ocean around you. That's pretty much exactly the problem that early astronomers were up against.
And that's the absolute heart of it. We're on a rock that's moving, looking at another rock that's moving. Both planets are constantly shifting, looping around the sun. Trying to untangle those two motions to see the real, independent orbit of Mars, that was a truly monumental challenge. To crack this nut, astronomers like the legendary Johannes Kepler had two key bits of info, thanks to his mentor, Tycho Brahe, who was obsessed with observation. First, heliocentric longitude, which is just a fancy way of saying where Earth is in its orbit from the sun's point of view. And second, geocentric longitude, where Mars appears to be in the sky from our point of view here on Earth. The real magic was how Kepler used those two different perspectives against each other.
And this is where the genius comes in. Kepler came up with this unbelievably clever way to solve that moving boat problem. He basically took the very thing that made it so difficult, the fact that everything is constantly moving, and he turned it into the key to the whole solution. It's just brilliant. Okay, so here's the game plan. Step 1, you look up and you mark where Mars is in the sky. Simple enough. Then, and this is the absolute key, you wait. Specifically, you wait 687 Earth days. Why that exact number? Because that's one Martian year. So Mars is right back in the exact same spot it started. But Earth, oh, we're in a completely different part of our own orbit. So you observe Mars again from this new vantage point. Now you've got two lines of sight pointing at the same object from two different places. And where those two lines cross, bam, that is the true fixed position of Mars in space.
Now imagine doing that over and over and over again, using years and years of data. This wasn't a quick aha moment. It was this incredibly slow, painstaking process of plotting one point, then waiting, then plotting another. But as he put each new point on his chart, a picture began to form, and it was a picture that was about to change everything.
You see, for thousands of years, everyone just assumed that planetary orbits had to be perfect circles. I mean, it's the heavens, right? It's got to be perfect. It's got to be divine. But Kepler's data, all those little dots he'd so carefully plotted for Mars, they just wouldn't fit on a circle. No matter how he tried to fudge it, it didn't work.
And this is it, the big one, his first law of planetary motion. The orbit is not a circle, it is an ellipse, kind of like a slightly squashed circle. And get this, the sun isn't even in the center, it's off to the side at a point called a focus. This idea just completely shattered centuries of deeply held beliefs.
We have a term for just how squashed an orbit is. It's called eccentricity. A perfect circle has an eccentricity of 0. Mars has a value of about 0.094. Now that might not sound like a huge number, and it isn't a super dramatic oval, but it was different enough to prove that the universe didn't run on the perfect circles everyone thought it did.
And this elliptical path has another cool consequence. It means Mars's speed actually changes throughout its year. When it gets closest to the sun, that's a point called the perihelion, gravity's got a stronger grip, and Mars just whips around its orbit. But when it's at its farthest point, the aphelion, it kind of takes its time, moving much more slowly. That's the essence of his second law.
So, okay, cool history lesson, right? But why does any of this 400-year-old discovery actually matter today? Well, here's why. Every single mission we send to Mars, or anywhere else for that matter, is built on the foundation of Kepler's laws. They are quite literally the rulebook for how to travel through space.
When NASA plans a mission, they aren't just pointing a rocket at a red dot and hitting go.
They are performing this incredibly complex orbital ballet, using Kepler's laws to calculate the precise elliptical path a spacecraft has to take to meet up with another moving planet hundreds of millions of miles away.
The journey for the Curiosity rover, for example, took about 255 days. That's over 8 months hurtling through the vacuum of space, all following a trajectory calculated with math that's been around for centuries.
And it's a fair question, right? It seems so much simpler to just point your rocket at Mars and fly straight there. Why all this complicated orbital stuff?
Well, here's the catch, and this comes straight from the people who plan these missions. You can't just aim for where Mars is now. You have to aim for where Mars is going to be in 8 months when you get there. If you flew in a straight line, by the time your spacecraft arrived, Mars would be long gone, and you'd just be sitting in an empty patch of space.
And Kepler's legacy doesn't even stop when we get to Mars. It fundamentally influences how we operate once we're on the ground. Understanding the planet's orbit and its environment is absolutely critical for every single engineering decision we make.
Just take a look at the power sources for these different missions. You see a really clear split. The earlier missions like Spirit and Phoenix ran on solar panels. They were way cheaper. But look at the mission length. The Phoenix lander lasted less than half a year. Then you have Curiosity and Perseverance. Yeah, they cost a lot more, but they run on radioactive batteries, and they've been chugging along for over a decade.
And this really gets to the heart of the challenge. Solar panels are lighter and cheaper, which is a massive deal when you're launching something off the planet. But on Mars, massive dust storms can blot out the sun for weeks. The seasons, driven by that elliptical orbit, mean less sunlight at certain times. They're just not reliable for the long haul. Those radioactive batteries, on the other hand? Yeah, they're heavier and way more expensive, but they provide a constant, steady stream of power for years and years, no matter what the Martian weather decides to do.
So every single one of these huge decisions, what kind of power to use, how long a mission can last, what instruments it can carry, it all traces directly back to our fundamental understanding of Mars's journey around the Sun. Knowing about its seasons, its distance, and the conditions on its surface all stems from the work that started with Kepler just trying to make the dots line up. It's just incredible when you think about it. Kepler completely rewrote our map of the solar system with basically just pen, paper, and a whole lot of patience. Today, we have robots on the ground and AI that can analyze more data in a minute than he saw in his entire lifetime. So it really makes you wonder, if he could uncover the laws of the cosmos with such simple tools, what profound new discoveries are waiting just around the corner for us?